So in this module, we're going to focus on ionization energy. I know it says and electron affinity. That's actually going to be in the next module if you need to watch that one. But for this one, we're going to really focus on ionization energy. So what is ionization energy and what trends do we see? Ionization energy is defined as the energy required to remove a valence electron. Technically, it can be any electron. It doesn't have to be just valence. But an electron from a gaseous atom or ion. Now, we do start with the valence electrons and then move towards the other electrons. You're going to start with, whatever is the most highest energy electron and then keep removing, but it doesn't have to be a valence electron. We can see a picture here that kind of shows some different metals, that specifically our alkali metals. Remember, alkali is group 1. And their energies. And so we see, lithium, sodium, potassium, rubidium, comparative to their noble gases. So group 1 to group 18. And so each one is compared to the noble gas in its row, if that makes sense. So like lithium comparable to helium, lithium comparable to neon, they're both in the N equals 2 row. Sodium to argon are both N equals 3. Potassium to krypton, N equals 4. Rubidium to xenon, N equals 5. What we see here is that there's a large increase in energy for the next ionization energy. The other little dots in here represent the other elements in between. And so we're going to talk about how we can figure this out and how you guys should be able to predict these trends. First, I want to ask you guys a question. How is this trend related to the atomic radius trend? Well, the general trend for ionization energy is it increases across and up the table. Atomic radius increases from right to left and down the table. So the truth is, it's completely opposite. Ionization energy, again, the energy required to remove an electron from a gaseous atom or ion. It is an endothermic process. Endothermic, again, meaning that we have to give it energy to happen. So even though we talk about how, or I have told you guys repeatedly now, alkaline metals want to lose 1 electron. Alkaline earth metals want to lose 2 electrons. Metals in general want to lose electrons. They all want to form cations. It still takes energy to do so. We still have to pay a price for that. It's not just going to give up the electron. It is going to cost something. It just doesn't cost a lot. Endothermic means delta H, or your enthalpy, so heat of reaction, is greater than 0, just meaning it costs, and heat of reaction is related to energy, and so it costs to remove that electron. You do need to be able to write these equations. So we see here for lithium, these are in the gas phase, by the way. It does say gaseous here. It does need to be a gaseous atom or ion to remove an electron. We see here lithium gas going to lithium plus an electron. We can do this for any species. We could say zinc gas going to zinc plus gas phase plus an electron. Zinc plus gas going to zinc 2 plus gas plus an electron. So if you see anything in the gaseous phase, on your reactant side, and on the product side, you see it as an ion with 1 charge higher than it was before, plus an electron, you're probably looking at ionization energy. And you'll usually report this with some kind of ionization energy value. So first thing you need to know is outer electrons are not held as tightly by the attractive force of the nucleus because they're shielded by the inner core electrons. So outer core meaning your valence electrons first, and then in through your core into your inner core. What do I mean by inner core? I mean the closer I am to the nucleus, the tighter it's held. The farther from the nucleus, the weaker that hold on the electron. This is the opposite trend from atomic radius, though. I know I said that on the previous page, but just so you've got that written down. Large atoms have smaller ionization energies. Why? Why does a larger atom have a smaller ionization energy? Well, we need to remember, what does ionization energy mean? It's that energy required to remove the electron. If an atom is really large, to be honest, it just doesn't take as much energy to remove the electron because it's so far out from what the atom is really holding on to. When we get far enough out from the center of a nucleus, so you've got your nucleus here. Let's say we've got n equals 1, n equals 2. These should be circles. N equals 3, n equals 4, n equals 5. By the time I get out here to 5, this electron is really shielded. It's shielded by all the electrons in the middle. And there's more of the electrons that I'm drawing here. I can't fit them all in. This electron, wrong button, sorry. This electron is very, very shielded from the nucleus, which means it's feeling the pull of the nucleus the easiest, which means it's the easiest to remove that electron, the easier to remove the smaller ionization energy. The other thing you need to know is just the convention of writing them. If I write IE1, that's the energy to remove the outermost electron, or the first electron. IE2, the second electron. IEN is the nth electron. So if it's at IE9, that would be the 9th electron. So I know the picture over here shows us the values already, but let's talk about this. What about the ionization energy of sodium? The first ionization energy versus the second ionization energy. What that means is removal of the first electron. So IE1 for sodium. We've got sodium in the gaseous phase, giving me sodium plus gas plus an electron. The ionization energy here is 496 kilojoules per mole. That's what I've got listed right here. The second ionization energy, though, so if I took Na plus gas and formed Na2 plus gas plus another electron, the second ionization energy here, 4,560 kilojoules per mole. We see a huge, huge jump. So what I want to ask you here is, which of these is larger? Well, we can say by looking at numbers that our second ionization energy is higher. But what if I didn't give you those numbers? How are you going to determine that without those numbers? I want you to think about how this atom or ion is constructed. What do we have here? Think about your electron configuration. Sodium has an electron configuration 1s2, 2s2, 2p6, 3s1. Sodium 1s2, 2s2, 2p6. Or sodium second one, sorry. This is second removal, second ionization energy versus first. So this is the Na plus going to Na2 plus an electron, where everything's in the gaseous phase. And this is Na going to Na plus an electron. If you think about the electron configuration and also your Z value, how many protons do you have? Sodium has 11 protons. Here, 11 protons are holding on to 11 electrons. Here, 11 protons, write that so you guys can see it, 11 protons are holding on to 10 electrons. It's going to take more energy to remove one of the electrons when it's only holding on to 10, because each of these electrons here feel the pull of that nucleus a little bit more than over here. But how else can I look at that? How can I follow the trends here? I want you to think about the atomic orbitals. So I want you to draw them out on an energy scale. You can draw out just the last two. We're going to draw out the 2p's and the 3s. The first thing I'm talking about ionization energy of 1 is removal of this electron. If I remove that electron, that is the only electron still residing in the n equals 3 energy level. Now, the other way to look at this is with the circles. N equals 1, n equals 2, n equals 3. I'm going to use dots. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, and 8. And then 1 electron out in the 3rd energy level. If I lose just that last electron in that 3rd energy level, now my n equals 2 energy shell is completely full. My n equals 3 is completely empty. I've removed this electron, and this is more stable. But that second ionization energy that we're talking about removing, now I'm removing one of these electrons. I'm removing one of your core electrons. I'm removing this electron. I need to undo not only a completely filled p shell, but I also need to undo a completely filled n equals 2 shell. It'll do it, but you better pay it a lot to get it to do so. It's going to take more energy than it would to remove the first one. I want you to draw these out. I want you to think about that process and think about why does that make sense. What about this first ionization energy of magnesium and the second ionization energy of magnesium? We're going to think about it in the same way. So let's go ahead and write out what those reactions are. So first ionization energy, magnesium gas, going to Mg plus gas plus an electron. And the ionization energy here is 738 kilojoules per mole. The second ionization energy, Mg plus gas, going to Mg2 plus gas plus an electron. The energy is 1450 kilojoules per mole. So this and this. Now, what I see here is that the first ionization energy of magnesium is higher than it was for sodium, but the second one's a lot lower. I've told you that magnesium wants to lose 2 electrons, though, to be like a noble gas. So why does it cost more to lose the first electron? That comes back to understanding how these are constructed. First, let's think about answering the question. The one that's got which one's larger? IE2 will be larger. It's always going to take more energy to remove the second electron, no matter what, okay? It's always just going to take some more energy. But why do I see such a discrepancy compared to the sodium? You can think about this in terms of electron configuration or atomic orbitals. So let's go ahead and do both. For magnesium, our Z value is equal to 12. Magnesium has 12 protons. Our electron configuration, 1s2, 2s2, 2p6, 3s2. So we've got 3s, 2p. Our 2p's are completely full. Our 3s is also full. This is for magnesium. So for magnesium, the first electron it needs to lose is this electron in your s orbital. That is paired up. Now, s orbitals aren't very powerful overall, but it is a full-filled shell, full-filled subshell, full-filled s subshell. So it does take more energy than compared to sodium. This one's going to take more because we need to unpair right now we've got a filled S subshell for magnesium. But once I get rid of that first electron for magnesium, all that's left now is just one more electron. This is still a valence electron. Hence why it takes so much less energy than the second electron for sodium. What about the third ionization energy for magnesium compared to the second? So the first ionization energy, second ionization energy, third ionization energy. The third ionization energy is huge because this is a core electron. We're now removing a core electron, and it's going to take a lot more energy to do so. Okay, there are exceptions to the rules that you need to understand. So what are the exceptions and why? Well, first, between groups 2 and 3. Why is there an exception between groups 2 and 3? Because it is easier. Or sorry, I say 3, I mean 13. It used to be called group 3, I apologize. Basically, the rule that starts with beryllium and the rule that starts with aluminum. It is 13. It is easier. To remove a higher energy P electron than a lower energy S electron. So what I'll find is that going between group 2 and 13, group 13, it's easier to remove that electron. We also have discrepancy between groups 15 and 16, and this is due to 15 has a half-filled shell. So, if we think about nitrogen, nitrogen has a half-filled shell. To ionize nitrogen, you have to break up a half-filled subshell. This costs more energy than you would expect because this has a special stability. When you ionize oxygen, you get a half-filled subshell. So ionizing nitrogen is going from this to this, you're destroying that half shell. For oxygen, you're getting rid of this electron, you're forming a half-filled shell. So oxygen actually costs less energy than you would think it would because, well, you know, it's going to form a half-filled shell. Yes, oxygen wants to gain 2 electrons. It wants to be like a noble gas. But if it has to pick the battles, it's going to, you know, if your only option is stay as you are, give away one of the electrons, it will give away one of those electrons to get that half-filled shell. It's going to cost you less energy than you would expect. So let's work through some examples here, just to make sure you guys are comfortable. Which is greater and why? The first ionization energy of magnesium or the first ionization energy of aluminum? What I want you to do this is think about the electron configuration, if needed, the atomic orbitals. So for magnesium, our valence electron is 3s2. Our aluminum, 3s2, 3p1. Write out 3s, 3p. It's for magnesium. And for aluminum. So I want to know which is greater and why. Removing this electron or removing this electron? What do you guys think is going to be a larger value? Hopefully you picked magnesium. this is one of those exceptions. This is group 2. This is group 13. This is higher in energy. It's easier to remove that high energy p orbital that's hanging out all by itself than it is to remove a lower energy s electron that's also paired up in a full-filled s shell. What about aluminum and silicon for the first ionization energy? Well, aluminum, we know we just wrote 3s2, 3p1. Silicon, 3s2, 3p2. So how do these go together though? Well, let's redraw it. Aluminum and silicon. Aluminum and silicon. I want to know which is greater and why. Is it going to take more energy to remove this one aluminum or more energy to remove this one silicon? This may be a little complex to think about. You can always think about the number of electrons something has. So aluminum has, 10, 13, a Z effective of 13. Whereas silicon would then be 14. So this has more protons holding together these electrons. This has less protons holding together the electrons. That's one way you can think about it. Another way you can think about it, and that's probably the easier way for most students, the other way to think about it is that if I lose just this electron here for aluminum, now I have an empty 3p shell and full 3s. If I get rid of this electron here for silicon, I still have an electron in my 3p. So it's not that it won't give it away, it's that it's not as advantageous to give it away because it still would have to get rid of a second electron. So for that reason, silicon will have a higher first ionization energy. What about the first ionization energy of phosphorus versus sulfur? Phosphorus, 3s2, 3p3. Sulfur, 3s2, 3p4. So Z here would be 15. Z here would be 16. It's always good to factor in your Z values. Often, not always, often a higher Z will lead to a higher ionization energy. This is an exception to that rule. This is also an exception to that rule. The reason here is that is supposed to say the word exception. The reason here that the higher Z value is actually not going to have the higher ionization energy is because of the other exception we told you. The difference between the two groups. Well, let's draw these out and see why that matters. Phosphorus versus sulfur. 3s, 3p, 3s, 3p. I'm talking about this electron or this electron. For phosphorus, if I take away this electron, I have destroyed a half-filled shell. Half-filled shells have more stability. For sulfur, if I take away this electron, I've created a half-filled shell. That's actually going to take less energy than you think it would, hence the first ionization energy of phosphorus will actually be higher. Okay, what about sulfur versus chlorine for its first ionization energy? Sulfur, 3s2, 3p4. Chlorine, 3s2, 3p5. Z value here, 16. Z value here, 17. Okay, so is it going to take more energy to take away this electron here or this electron here? Chlorine is going to take more energy. If chlorine loses that one electron right there, so I take this electron away, and I form chlorine plus, versus taking away this electron, and forming sulfur plus. When I take that electron away from sulfur, I form a half-filled shell. For chlorine, still partially filled. It's going to take, so it's kind of like, well, why are you going to take my electron away if you're not even going to give me a half-filled shell? What was the point of that? How about you just give me an electron and I have a full-filled shell? So chlorine's kind of upset with you. What about the 6th ionization energy of sulfur versus chlorine? So this would be the 6th electron removed. Let's count backwards. 1, 2, sorry, I counted that wrong. 1, doesn't really matter on that, but 1, 2, 3, 4, 5, 6. That would remove all valence electrons. Versus 1, 2, 3, 4, 5, 6. That would remove all but one 2s electron. This is going to be higher. Let me do that a slightly different way and actually erase it so you guys can see what I mean. For sulfur, we've got 3 P's at the top. Three S. And then under here we have your 2P that are completely full as well. Chlorine, your 3P. Your 3S. Your 2P. So for sulfur, I would first remove this first electron here. 1, 2, 3, 4, 5, 6. If I remove 6 electrons, I have an empty 3s shell and a full n equals 2 shell. Empty 3s, 3p, completely empty n equals 3. And n equals 2 is completely full. Chlorine, 1, 2, 3, 4, 5, and 6. That 6th electron is unpairing a full 3s shell. Now, yes, the S's overall aren't the strongest thing in the world, but it was full, and you unpaired it. It's going to take more energy to do that. What about the 7th electron? Well, let's add these all back in. And let's count backwards. 1, 2, 3, 4, 5, 6, 7. Now you're removing a core electron. For chlorine, 1, 2, 3, 4, 5, 6, 7. All you've done is remove the last of its valence electrons. The 7th electron from sulfur is going to take more because it is an inner core electron or core electron. Last thing I want you to look at, place the following in order of increasing first ionization energy. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. I'm going to give you the answer for this one, and I want you guys to see if you can tell me why. To answer this question, I want you to think about the electron configurations. Your Z is number of protons, and see if it makes sense to you how we get this trend for the first ionization energy of each species specifically.